Hello everyone, today we're going to cover electrical conductors, insulators and semiconductors. So this is our first topic in module number 2. If you're looking for it, that's where it is. The module name is Direct Current Fundamentals. So now we've covered off our legislation stuff, health and safety, all of that kind of stuff, and we're going to move into the real stuff, electricity, how it works, what it does, and we're going to start by looking at conductors. So let's have a little talk about atomic theory. So when we talk about atomic theory, what we're talking about is the actual physical thing that's happening when electricity is flowing, when current is flowing, voltage is applied to a conductor, all of that sort of stuff. Now, it's in terms of the importance of this to your day-to-day activities as an electrician, it's not really important at all. There's nothing that you can do with electrons. You can't see them, can't touch them, can't manipulate them. So the actual practical relevance of understanding what's happening at an atomic level is fairly obscure. However, in saying that, to be a good electrician, you need to understand electricity. If you don't understand electricity, then how can you go out and do your job? So this all is part of building our knowledge of how electricity actually works, and then we build on top of that into how that affects us on a day-to-day basis. So if we look here, we've got a little diagram of an atom. Lovely little diagram at the bottom here. The atom is the smallest part which an element can be separated into. So it's the smallest thing we know of. Well, there's other stuff, but for practical purposes, it's the smallest divisible unit of matter. Atoms consist of positive and negative charges. So the different particles within the atom have different charges, either positive or negative. Positive charges are called protons, and they are contained in the nucleus. That's in the center. So that's our little guy down in the middle here. Our protons live in there. And the negative charges are electrons, which orbit around the nucleus. So these are the electrons shooting around in orbit around the proton. They are bound to the nucleus by the force of attraction between positive and negative charges. So the positive charges in the nucleus attract the negative charges on the outside, the electrons, and the electrons remain in orbit. This is a convenient way to draw it. That's not what an atom actually looks like. It's nothing like what an atom actually looks like. But it's convenient for our purposes. The valence of atoms. So the outer electron shell of an atom is called the valence shell, and the number of electrons in that shell determines the valence of the atom. So every atom every element has a different number of electrons in orbit around the nucleus, and the number of protons or electrons that an atom has determines what material that thing is. If you think about it in the sense that a proton and an electron are the same. It doesn't matter which atom they're living in, which type of atom they're living in. An electron and a proton are the same. All protons are the same, all electrons are the same. The difference between two materials, let's say copper and silver, is the number of protons and electrons each of those things have in an atom. So different numbers of protons and electrons determine the nature of that material, and that's what we call elements, is the pure form of an atom or of a material with only atoms of that type together to create a thing that we can see, touch and hold. So electrons orbit around the nucleus in shells. If you think about it like planets orbiting the sun, there's X amount of planets on the central orbit, and then the outer orbit, and then the next orbit, or whatever, depending on how many electrons determines how many orbits there are. And the outer, how many there are in the outer shell determines the valency of the valency of the atom. Valency is important because each shell has a predetermined number, so there's a certain amount on the first and second and third. So if you have very few electrons in the outer shell, then there's spaces for more electrons to come in, so as a low valency. If it's got a high valency, that means that the outer shell is full or almost full, so there's not many spaces for electrons to come in. And why is that important? Well, if we look at the movement of electrons, materials like copper and aluminium have free electrons in their outer shell, known as the valence shell, so they've got free electrons in the outer, and if electric charge is applied to these, the free electrons will move from atom to atom. And this electron movement is what we recognize as the flow of current. So if you think of a piece of copper as being a whole bunch of copper atoms bound together, when we apply current to that, remember that our electrons and protons are physically charged, so they've positive and negative charge. So we apply a charge to that material, positive and negative charge to either end of that material, then we're going to affect the behavior of those electrons, because now that negative charge in that electron is either going to be attracted or repelled by the charge that we're applying to it. And so electrons can jump from one atom to the other. And in a way, you can think of this as in the process of electric current flowing as like pool balls smashing into each other. If I've got a long line of pool balls and I hit one, it's going to hit the next one, which will hit the next one, which will hit the next one, and so on and so on. And eventually the last one in the row will roll off. So that's kind of what's happening. It's a good analogy for what's happening when we have electric current flowing through a material like copper, is that the electrons go bouncing from one atom to the next atom, to the next atom, boom, boom, boom. And then because that electron has a charge, that negative charge bouncing along, then we have a flow of charge along that material as the electrons bounce down and bump each other onto the next one. So conductors are materials that have 1 to 3 electrons in the outer shell orbit, which are loosely bound to the nucleus and therefore easy to remove and can conduct electric current. So because there are not too many electrons in the valency shell, then they're easily movable, which means that when we apply that charge, those electrons are going to easily jump from one atom to the other and conducts electricity. So it's a conductor because it conducts electric flow, or it allows the flow of electrons to move through that material very easily. Typical conductors and uses. We have gold for contacts and electronic components, especially audio and switch contacts. So there's gold in a lot of electronic things, cell phones and that sort of stuff, because gold's a really good conductor, and it is highly resistant to corrosion. So we can use gold in situations where we don't want our conductor to corrode. Obviously, we're not making cables out of gold because it's very expensive. So generally, you'll see that like gold-plated switch contacts and stuff. Very, very small amount of gold being used because obviously it's very expensive. Silver is used for contacts and switches and relays because it's a very good conductor, so it has many of the same qualities as gold. I believe silver is the best conductor that you can get. Also, it's quite expensive. Not as expensive as gold, but still quite expensive. Copper. Copper is used for flexible cords and wiring cables because it is a good conductor. So copper is a really great conductor. I'm pretty sure, if I remember correctly, silver and gold are slightly better, but copper is still a really great conductor, and it has the advantage over silver and gold that it's much, much, much cheaper. It's pretty easy to handle. It's pretty soft, so we can form it into long cables which are able to be bent and moved around and so forth. So I'm sure you're aware that copper is by far the most common conductor that we would use. Aluminium. We have aluminium for overhead lines and underground cable transmission lines. So aluminium's a pretty good conductor. It's not as good as copper. It again has an advantage over copper in that it's a bit cheaper. It's quite a bit cheaper than copper. It's not as easily malleable, so it doesn't move as easily as a copper cable would. It's a bit harder. But the main advantage that aluminium has over copper is it's much lighter. It's lighter and cheaper. So we use it for overhead lines, so power lines, and underground conductors. So same sort of thing, power lines but underground. That's because those cables need to be quite big. They need to be quite strong. Aluminium is stronger than copper. So if you replace an equivalent aluminium power line with a copper one, then the copper one would be much more likely to break. And then the cheapness of aluminium in those situations where they need to be quite big is important as well. The biggest downside of aluminium is it oxidizes rapidly. So in order for you to make a good joint with aluminium, you have to take the oxide layer off, but that oxide layer will develop again on top of the aluminium, typically within minutes. So it's not easy to join. You have to clean the aluminium first, put a paste on it to prevent the oxide layer coming back, and then quickly make your joint before anything goes wrong. Tungsten we use for lamp filaments because it can operate at a white hot temperature without melting. So inside a traditional incandescent lamp with a filament in it, we will use a tungsten conductor in there because we can have a very, very small conductor, which means it's a high resistance, so it's going to produce a lot of heat and light, but it will not degrade. If we tried to do the same thing with aluminium, copper, any of these other ones, it'll melt really, really quickly. So tungsten has that advantage of being able to withstand very, very hot temperatures. Carbon we use for commutator or slip ring brushes. When we start talking about motors and generators, we'll learn more about commutators and slip ring brushes. But carbon, and we're talking carbon like look, when we talk about carbon brushes or carbon conductors, it looks like pencil lead, the lead inside your pencil. It's reasonably high resistance, but it's good for a conductor where the conductor needs to be touching something moving. So inside a motor where we need electricity onto the moving part of the motor, then if we can't join a wire to it, when it spins, it's going to rip the wire off. So we have a carbon brush, which is just a block of carbon, which is touching against the spinning part of the motor. And as the motor spins, that carbon will slowly wear away, but not for in most cases many years. So we're able to have a conductor that is directly contacting a moving part, and it doesn't destroy it. Brass we use for terminals, connectors, earth and neutral bars inside switchboard. So that's a bar where we connect all our earths and our neutrals inside a switchboard. And nichrome is used for heating elements because it has a high resistance, much like tungsten. We need that high resistance where we want to create heat because resistance dissipates heat. So we have high resistance elements created, built out of, or using nichrome as the heating element, as a conductor, because it has that good high resistance. So we have a little table here that gives us some information about the kinds of conditions or the environmental factors that we would consider when we use specific types of conductors. So if we have if heat is a problem, then we're going to use tungsten, carbon, or nichrome because they have very high melting points. And we're talking about not so much environmental heat, but heat caused by the current flow. If there's moisture present, gold, brass, lead, or tin, because they're all very good, very high resistance to corrosion. Corrosive materials, so acids or chemicals, we use brass, gold, lead, or galvanized iron. It's all very resistant to corrosion. Dust does not affect any of our conductors. Tension, so that's when we've got hanging lines like a power line or something like that, anything that's hanging, so it's going to be pulled. We would use hard drawn copper or aluminium because they have strong tensile strengths. Aluminium is better than copper in that regard. Compression, so if the conductor is going to be squeezed anywhere under compression force, again we would use copper or aluminium. And it says that you can use crimping lugs. So one of the ways we might connect to a copper conductor is to have a sleeve or lug, as we call it, which we'll see when we start doing some installation stuff, that we squeeze around the conductor. And vibration, so if we have our conductors in a place where there's going to be a lot of movement, stranded copper wire or carbon brushes to give us the ability to be flexible and movable. So insulators, that's conductors. We'll certainly cover more about resistance and conductors and that sort of stuff, but this is just a brief outline and introduction at this stage. Insulators are materials that have 5 to 8 electrons, so more than conductors, in the outer valence shell. and they are tightly bound to the nucleus, and therefore they're not easy to remove, and therefore don't conduct current. So what we're saying there is that because there's more electrons in that outer shell, they're harder to move. There's fewer gaps. So when we apply a current, we're not going to have those electrons start bouncing around easily and therefore conduct electricity. These are materials that will resist the movement of electrons. So we can use them as the opposite of a conductor, right? And insulators are just as important as conductors are, because wherever we're conducting electricity, we need to insulate people from it. So typical types of insulators: glass. We use glass as an insulator. We have glass fiber tape on conductors, or high voltage power line insulators. If you have a look at where a pylon, and you'll see that where the cables are connected to the pylon and they hang down underneath, you'll have these ring looking things that hang down. Those are glass insulators, so they prevent the conductor itself from contacting or transmitting electricity to the pylon, obviously, because we don't want people touching pylons and getting belted by 11,000 volts or something. PVC, it's polyvinyl chloride, so it's your standard plastic insulation that you see everywhere. So it's conduits, flexible cords, cables, and cable sheets. So any cable that you see will most likely have a PVC insulation. It's the most common type. Rubber, it's not used as much anymore, but it can still be used for flexible cords, fixed wiring, and sub-zero conditions. So in regard to flexible cords and fixed wiring, it's not used often. You will still find rubber from time to time. Certainly in older buildings you might find rubber. The downside of rubber, the reason we don't use it, is that it does degrade over time, as opposed to PVC, which doesn't really. So if you ever find wiring in a house that has rubber insulation, you'll usually find that if you touch it, the rubber will start to fall away from the conductors immediately just by moving it. That's because we haven't really used rubber for about 40 or 50 or 60 years even. So all of that rubber cable is really old. As long as you leave it alone, it's fine. As soon as you move it, the rubber will start to fall apart. So we don't use rubber anymore, and be very careful when you come across old rubber cables, because as soon as you touch them, you're going to have to replace them, because they will destroy themselves immediately. Now, we will still find from time to time rubber cables made and used. So for flexible cords, we occasionally use rubber because it is much more heat resistant than PVC. So if we need a flexible cord that's going to be used in a really hot situation, then rubber is better than PVC. It's also much better cold resistant than PVC, so we may use it in very low temperature situations as well, because it will still retain its elasticity even when it gets very, very cold, whereas PVC, when you get to about zero, it becomes pretty hard and your flexible cord is not really flexible anymore. So mica is like a white ceramic looking thing. We use those in toasters, irons, heater elements, and supports and switchboards. Oils, so we can use some certain types of oil as a insulator, and we would use these inside transformers. So you have the big transformer case with massive coils inside there. We'll learn about transformers at some stage, and then to insulate the coils from the case, you can fill that thing with oil. The advantage of using oil as an insulator in that situation is that it's good at dissipating heat. So if you're generating a lot of heat in those coils and you want to remove that away, that oil used as an insulator will also help to cool that. As it moves around, it'll dissipate heat coming off the coils. Magnesium oxide, we use that as a powder. We use it inside elements on a stove or oven or hot water cylinder or in your jug or anything like that. So you see that you've got the metal outer, like in your the element on top of your stove, and if you cut that, you would find it's filled with a white powder, and then the actual element itself is inside that white powder, and that white powder is used as an insulator in that case. Obviously, it's very, very heat resistant. We could not use PVC or rubber or any of those other things as a insulator in this situation inside a heating element, because it would burn, it would just be destroyed. So magnesium oxide is heat resistant. We also use it in MIMS cable, which is mineral insulated metal sheath. Also referred to as pyro cable. This is very, very rare these days. You don't see it very often. I've never worked on it. I've seen it, but I've never worked on it. What MIMS cable looks like a copper pipe, a very small copper pipe, and it has conductors in there, and again it's filled with the white powder used as an insulator. It is extremely heat resistant, so you can use mineral insulated metal sheath or essentially in situations where that cable may even be exposed to fire or direct heat. It's not quite the same as a heating element because it's not designed to create heat, it's just used as an ordinary conductor, but in situations that are going to be very, very hot. Ceramics we use for cable supports and standoffs, fuses and terminal blocks, so just ceramic insulators that you use to screw a conductor to or a terminal board or something like that, so it doesn't touch whatever you're mounting it to. And we use air as an insulator. I've talked about this before in class, that if you think about a bare conductor for a power line, it has no insulation around it. It's not covered in PVC or anything. It's just hanging free in air, but air is the insulator in that case. So here are the environmental factors for consideration when selecting insulators. So glass, mica, ceramic or PVC have high melting points. Glass or PVC don't absorb moisture, so they're really good in wet situations. Corrosive materials, glass or ceramic, are resistant to chemical. Dust doesn't cling to glass or ceramic, so if you've got issues with dust, it's a good idea. Tension, under tension, glass fiber is really strong against tension. In compression situations, we've got that squeezing force, high temperature PVC or fiberglass covered sleeve. And vibration, PVC again, and you can see that PVC is in most of these, because that's why it's a really common and useful insulator. Or oil, and as I said before, there's some heat dissipation reasons why we could use oil, but also in that situation where you've got movement, then the oil is not going to fall apart. It's oil, it's not a solid object. Semiconductors. Now we're going to do a lot on semiconductors in module 5, so don't freak out about it too much now, but just as a brief introduction, semiconductors are materials which have electrical conductivity halfway between that of a good conductor and a good insulator. There are many types of semiconductor materials, but the two most frequently used are germanium and silicon, and of this, silicon is the most common. So a semiconductor, or what we do with semiconductors, is generally electronic applications. So semiconductors are the working parts of electronic, like transistors, diodes, virtually any electronic part that you can name, and the semiconductors are created in a way that each of those devices have a different function. As I said, when we get to module 5, it's all about electronics, so we're going to cover all of these things, and we'll go into depth on semiconductors. But for now, it's worth just saying that they conduct in some situations and not others. Semiconductors conduct in some situations but not others. So we use semiconductors to create semiconductor components, as I just said. So P-type and N-type semiconductors, so that's a positive or a negative type semiconductor, two different styles, can be fused together to form various components for use in electronic circuits. A junction of a P-type and N-type produces a P-N junction diode for use in rectifier circuits, and transistors are three-layer devices that can be NPN or PNP. Other common electronic components are silicon-controlled rectifiers and triacs. Now, as I said, we're not going to go too much into depth on those. But as I said, we can have a semiconductor, a piece of semiconductor material that will conduct in some situations and not others, or it may conduct in one direction and not others. When we get a positive semiconductor and a negative semiconductor and we join them together, then we can start to manipulate things by using different voltages, and positive on one side, negative the other, or vice versa, to make that thing do interesting things, like conduct when I put a voltage here, but not conduct when I put a voltage here, for example, which gives us a sort of a one-way valve, like a diode, which we have had a brief look at. So a diode is just a positive and a negative together. It will conduct in one direction, but not the other. So semiconductors, very, very, very useful. Quite a difficult concept to get your head around. Don't freak out about the details of it now. We'll certainly cover that later. So that is it for this lesson. So that covers off a very basic level. What is a conductor? What is an insulator? What is a semiconductor? And as I said, all of those things will be covered in far more detail in future modules. But that is it for today. Kia ora, thank you very much, everybody.